And so again, I want to welcome the attendees that trickled in after the first set of introductions to this Future Leaders in Robotics and AI Celebrating Diversity and Innovation Seminar Series sponsored by the Microsoft DC Metro Engineering site. Our next speaker is going to be Benjamin Riviere. He's a PhD student at the California Institute of Technology, studying with Professor Sung-Yu Shang. He received his bachelor's in mechanical engineering from Stanford University in 2017 and a master's in aeronautics from Caltech in 2018. His research interests are in the intersection of planning, learning, and dynamical systems with application in robotics, space autonomy, and self-driving cars. He has received multiple awards, including honorable mention for best paper, the IEEE RAL, best graduate student, the GNC paper at AIAA SciTech, and was selected as well as an RSS pioneer. And so with that, I'm going to stop sharing and let Benjamin share. The floor is all yours.
Thank you for inviting me. I'm excited to be here and for the introduction. Okay, great. Yeah, so thank you for being here. I'm excited to present my work. What do robots dream of? Search-based decision-making and control for continuous systems. So here are some robot videos that I'll show throughout the talk. And I kind of wanted to talk about them just at a high level before we get into it. What unifies them is the robots are learning on the go. So it's not like a pre-trained offline solution. It's not a manually designed prescriptive solution. It's the robots are in real time searching through the space of what they could possibly do and discovering optimal behavior for themselves. So this kind of flexible, this kind of like decision-making framework is basically more flexible and lets you solve a larger class of problems and handle more types of uncertainty and do more things with robots in real time. So the talk outline is as follows. I'll talk about search-based decision-making control and what it means and why it's a good idea at the beginning. And there's three kind of reasons why I think it's really a good framework for solving these types of problems. The first is that you have notions of global optimality, so you understand why the robot is learning. And the other two I won't dive into in detail for the purpose of time, but you can guarantee things like stability and you can synergize well with deep learning. So this is actually the connection to the heuristics, the Kahneman system 1, system 2 that Krishna talked about in the previous talk. This is kind of my connection to it as well. I'm happy to follow up with that. The big kind of gap in search-based decision-making and applying it to physical systems is that search is a naturally discrete algorithm. And so there's a lot of work that needs to be done to bridge the search-based algorithms into the continuous world. So I have work where we kind of search for systems with dynamics, and that's the main work that I'll talk about today. But we also have work where we search with uncertainty, and we search for multiplayer games, and there's different ways to kind of handle these kind of elements of continuous spaces. And then with these like technologies that we develop to bridge these gaps, we can control systems with complex dynamics, like flying a quadrotor through a wind field. We can make a spacecraft resilient to faults in its system components, like its sensors and its actuators. And we can control multi-agent systems and self-driving cars. So let's dive into the first part of the talk, which is search-based. What is search? So this is my kind of visualization of search. Search is the design of simulated futures, dreams, such that the realized trajectory is optimal. So this is why I called my talk, What Do Robots Dream Of? It's in reference to the simulated futures. The simulated future is the orange process, and you try to control that orange process such that when the robot actually chooses to do stuff, shown in blue, the blue process is optimal. And this is a good framework, but it doesn't work well for continuous systems. So here we have, oh, sorry, I forgot to mention what these plots actually were. This plot on the left is the state space. So it's a robot that starts at the blue square and tries to go to the green square. And on the right is an action space representation of it. So it looks more like a traditional decision tree. If we try to take the same problem and we try to move into continuous spaces, so we try to take a quadrotor that lives in a continuous world, and we try to get it to move over to the green goal area, and we use the same algorithm, the algorithm's not going to work. It's going to fail, and I'll talk about why it fails soon. But basically, search for continuous systems introduces new challenges. So both of these problems are instances of a decision-making and control problem. And there's a subset of these problems that are basically, let me try to hide this guy. There's a subset of these problems that are solvable with analysis, and there's a larger set of problems that are solvable with learning. And learning is like kind of a broad term, but what I mean by it is something like this. Like, this is a classical policy learning setup. You have a neural network and a robot, and you try to train the neural network to do the optimal thing for the robot. And the way that works is the network proposes an action, the robot executes the action, and then the state and reward feedback are used to train the policy. So this is a typical like process. It's like the learned policy becomes the optimal policy given data. And this is a good idea, and it works pretty well, but it's a little bit limited because it's essentially a black box process. It requires a large data set, there's no guarantees on behavior, and it's not interpreted. So search-based decision-making control kind of operates in the same input-output space as policy learning. It still solves a large class of problems. It still interacts with the real robot and learns from experience. But it's a little bit different because there's this extra phase of simulating the world. And so this extra step of simulating the world looks something like this. So inside of the actual search process, there's this exploration of a simulated robot. And based on the interaction with simulated data, the search policy will converge to the optimal policy. And this extra step of kind of building in this model of the physics of the robot, which can give you really important things like global optimality convergence, guaranteed stability, or synergy with deep learning. And mostly what I think this is all kind of a consequence of is it's exposing how the robot is thinking, and it's allowing us to analyze it, it's allowing us to make it better. And so instead of it being a black box, this is a clear box. So that's kind of it's like a clear box learning process is what search can be thought of. So what do I mean by global optimality convergence? This is the typical result for value convergence. It's called, this is the UCT result. It's like just a paper. It stands for upper confidence for trees, and it's the standard kind of search result for Monte Carlo tree search, which is the search algorithm that I use. It's basically on the y-axis, there's optimality, and on the x-axis, there's the number of simulated futures. So the x-axis can be thought of as data. So basically, as your data goes up, your optimality goes up, which is the expected trend. And the theoretical result is basically a upper bounding the optimality error, which is the same thing as lower bounding your value estimate or your optimality estimate. So next I'll talk about what are the terms in this actual formula here. There's like if we have a tree that defines like what kind of search process we're running, at the root of the tree, there's an estimate of the optimal solution. And the tree has a width and a depth. So it has some branching factor, it has some number of decisions it has to make. And those parameters, as well as the amount of data you have, will determine the curve here. And so when you actually run this algorithm, this UCT algorithm, it actually does not explore the tree uniformly. It explores areas of high reward first. This is called strategic exploration, and it's the technique that's used to prove this optimality. So kind of revisiting that previous example, the UCT result, where we just apply it for the quadrotor example, we got this kind of catastrophic failure. And one of our work that I'll talk about in a little bit is called sets. It's basically searching for the continuous system with continuous dynamics. And we can see the same optimality curve where it's like the optimality versus data. And our result is shown in orange, and the kind of naive result is shown in gray. And basically, the fact that we're to the left of this curve means that we have faster convergence. If for the same amount of data, we have a higher lower bound on our estimate. And just to kind of give a physical example of how much better our result is, if we take the same amount of trees, the same amount of nodes, and the same amount of data that we used to try to search for the planar quadrotor, and we apply it to the full 6 degree of freedom 3D quadrotor, and we give it a much harder task and a much harder environment, we're able to actually like smoothly come up with an intelligent, good solution. So that's kind of the gap manifested in like a physical example. So now I'll talk about I'll start talking about my actual work, which is and I'll dive into a little bit the details of how do you actually search for dynamics. So we've had this physical system, and I'm basically going to claim that the reason why it's not why the existing solutions don't work well on it is actually because it induces a very large high complexity tree. And because we know that the high complexity tree leads to a slow convergence, that's why this result isn't working. And that's what I'm going to claim. And basically, we can understand that this guy has a large search space because it has a high depth. So if you take a quadrotor, it has a fast attitude, which means that it can like rotate very quickly. That means you need to change your control very quickly. That means you need to make a lot of decisions. So then that basically the depth is going to be large. The second kind of contributing factor to the size of the search space is the width. So the width is basically how many actions you have to take, and the like standard discretization method is to take the action space and discretize it. And if you take like and in this table, the first row is going to be different action spaces, and the second row is going to be the number of discretized points in that action space. And so if you take a line and you take the corners, there's 2 corners. If you take a square, there's 4 corners. If you take a cube, there's 8 corners. If you take an m-dimensional cube, and instead of taking just the corners, you take eta points per dimension, you get the number of discretized points in the m-dimensional cube to be eta to the m. And basically, all of these factors, the width and the depth, contribute to the slow convergence. So with that in mind, I'm going to kind of present work here. It's called spectral expansion tree search that takes a regular tree search and modifies the expansion to be this kind of picture, which I'll talk about in detail, and that'll kind of address this issue. So the key idea is instead of searching over this very high complexity big tree and getting the slow convergence, we're going to search over a small tree and get fast convergence. But that's obviously not the whole story, because we need to make sure that these problems are actually, that the solution of the small tree is close to the solution of the big tree. So we start with this, to understand this, we start with this kind of lemma that says that the difference between these optimal solutions is going to be upper bounded by the distance between their reachable sets. So our goal in designing an algorithm is basically going to be designing something that creates a small tree and that controls the distance between the reachable sets efficiently. So before we can do this, there's a little bit of background. I'm going to talk about what's called the controllability matrix in the Gramian. Let's take a linear system. So this is a system z equals a z plus bu. And let's just step it forward in time. So z1 equals some function of z naught and u1. z2 can be written as a function of z naught and the control sequence. And we can roll that out until the hth z term. So basically, we have this equation for zh. It's a propagation of the initial condition plus a linear mapping times the control input. And this linear mapping, or the sequence of control inputs, this linear mapping is called the controllability matrix. It's a commonly used tool in control theory, in linear control theory, and it's useful for our purposes. And it makes total sense. It's the simplest possible idea you could have to connect the input sequence to the states. The next kind of idea that we have to bring in is this concept of the reachable set. We talked about the reachable set in the previous slide. We need to somehow understand the reachable set in order to prove what we want to prove. So it turns out, this is just a fact of linear theory, the reachable set is an ellipse with its center at the propagation of the initial condition, and its axes are parametrized by the spectrum of the Gramian, which is the controllability matrix times its transpose. So this is just like some facts about linear theory. So with that kind of being said, we're going to use those facts to compute our algorithm. So our algorithm looks like this. The first step is to exactly what we just talked about, computing the spectrum of the normalized controllability gradient. That's going to be we're going to be at some initial condition. We're going to normalize our system. We're going to linearize our system. So the linear system is shown in Z, and the nonlinear system is shown in X. And the blue dots are the spectrum of the gradient. Then we're going to draw the lines to the dots. These trajectories are linearly feasible. These are trajectories that are feasible under the linear system. This can be computed with a pseudo inverse and a rollout. And then the last step is to track the linear system with the nonlinear system. So here the nonlinear system is shown in green. There's a green reachable set. There's which is the boomerang looking shape. And there's the green trajectories. And so basically the green trajectories are synthesized by using a tracking control onto the blue trajectories. And that tracking control is kind of is constructed by using the discrete algebraic-Riccati equation, which is like a classical feedback control technique. We can prove that it contracts the dynamics, and therefore the distance between the green dot and the blue dot is bounded. So with this in mind, basically the point of setting up our operator like this is just to bound the reachable set between the green dots and the green boomerang, which will give us the result that we talked about earlier. So basically, theoretically, we can now run a tree search algorithm on the using the nodal expansion that we just talked about, and we can get the result we wanted, which is like these small trees that are representing the problem correctly. So the theorem is a direct application of the reduced width and reduced depth trees with controlled error from the supporting lemmas. We get this optimality error. We can compare it to the optimality error of the discretize then run search approach, and we just get a way better, way faster convergence rate. So now we can kind of reap the benefits of our theoretical labors, and we can talk about this this experiment. This is a quadrotor flying. We have a wind wall that's in the horizontal position, blowing wind upwards. The quadrotor is trying to visit each of the white targets while avoiding the orange obstacles. The tree is visualized projected downwards, but it's actually searching through the like 12-dimensional quadrotor dynamical space. What's unique about this problem is that the quadrotor is planning with knowledge of the aerodynamics. So the aerodynamics are this super complex function that we learn it beforehand. So it's modeled with the deep neural network, and the quadrotor is able to plan with the deep neural network in real time and solve this planning problem with these really complex dynamics. So the next two projects I'll just talk about very briefly, just to give like a flavor of what's going on. But this is the Search with Uncertainty project, and this is why we're interested in something like this. So if we have a spacecraft that's approaching a solar body, and its two retro thrusters have failed, and it doesn't know that to be the case. If we just like rolled out this system and we let the spacecraft kind of treat not think about its uncertainty in its state, it would try to activate its safety at the last minute, and it would collide with the object. So we kind of need to be aware of the uncertainty in the system while we plan, basically. The complexity of uncertainty is basically, instead of this tree being state action pairs, there's now belief, actions, and observations. So you need to reason about your uncertainty. You need to have a probability distribution about where you are. And so this is visualized in the picture here, where there's the tree that has different colored nodes now, and the belief distribution can be thought of as a Gaussian. And basically, you can step forward this belief distribution in the tree. And the challenge is that this Bayes filter, which controls the propagation of the belief, is hard to compute. And we found a way to do it analytically for this particular problem. So we were able to exploit some structure to do that. And using this structure, we were able to kind of create this algorithm, and we can roll it out, and we're the only ones that can solve this problem. So if you have a spacecraft with faulty sensors and the faultiness is going to compromise the safety of the spacecraft, our method that basically actively senses is the only one that can guarantee safety and in the presence of this kind of uncertainty in the dynamics, uncertainty in the model. The last example is searching for games. So the complexity of games is basically, if you think of it as like a turn-based game tree, this is kind of how the traditional game trees work, like chess game trees or the Go playing game tree. They all work like this. And if you need to reason over multiple players, like you iterate through all the players. So as you might imagine, now that we've talked about like the breadth and width of the game trees of trees and their effect on the convergence, we can look at these optimality curves again, and basically, as we add the number of agents, we get bigger trees, and then we slow down the convergence. So our solution to this, we can bias the tree with decentralized data-driven heuristics, and these heuristics can basically fight this blow up of complexity. The fact that they're decentralized means you can scale to a high number of agents pretty easily. So this is our hardware experiment for that. We have 3 quadrotors in blue trying to get to the taped region in the back left, and 2 quadrotors in red trying to tag them first. This is called the reach target avoid game. It's kind of a classical differential game that you can play. And what's unique about our solution is that the quadrotors are actually planning all of this in real time. And they're basically reacting to whatever the other agents are doing, and what their allies and what their enemies are doing in real time. So it's a closed loop solution, and it's not a prescriptive solution. Like they're solving the game in a very general way by just searching through everything they could possibly do and picking the best one. So my vision for future work is basically taking these ideas of search and actually unifying control and decision making. Like I think that as we get to more complicated control systems, it's going to become more important to bring in learning, and search is the correct learning framework to do this. So 2 examples are, we have this walking and flying robot called Leonardo at Caltech. And so this has like multimodal locomotion, and it's very common to control these systems with planning-based systems and learning-based approaches. So this is why it might fit in. The other example shown in the top right is an eVTOL prototype. So this means like a vehicle that takes off like a quadrotor and then flies forward like a plane. And in between that transition is actually very complicated from a dynamical perspective. So kind of bringing in learning is necessary because analytical techniques can't handle that. Decision-making robots, I'm really interested in getting robots to help for science. So AI for science applications. This example is a quadrotor that's sampling a volcano fumarole, and it can provide information to chemists about the composition of the chemistry of the volcano to make predictions about its state. It's potentially a dangerous operation, so it's it can help enable new science as well. And then the last picture here is the Dragonfly APL robot that will visit the moons of Saturn, and it basically represents a new frontier and resilience of autonomy. Well, I mean, like the Mars rovers already did something like that, but compared to the volcano drone, I think the gap here is it's more challenging because all of a sudden we have to have our systems just surviving by themselves, literally across the solar system. So yeah, that's the end of my talk. I want to thank my sponsors, my advisor, and my collaborators, and here are some references as well. So I'll stop there. Thank you.
Thank you so much. And again, I'll clap in lieu of the audience since they're not able to turn on their videos. A wonderful presentation.
Thank you.
I'll open up the questions for the speaker from the audience. Please use the Q&A feature at the bottom to post your questions. And while I give them a moment to do that, I'm curious about this last application that you showed with the reach avoid games. And you have this closed loop controllers, and I'm curious as to whether or not you've been able to, using these techniques, parameterize something about the games in order to kind of determine whether or not the pursuers are always capturing, the avoiders are always evading, or is it, what would the parameters, right, that dictate the performance?
Right, so that's a great question. We kind of we played with a couple different things. I think that one thing that was really fun to play with was the dynamic limits of the people. So we might like do a 3v1 game, but the defender is like very agile or something like that. And he might be able to capture 2, or all three of them for a poorly trained policy. But if the three slow guys collaborate in a very unique way to like spread out a lot, then it might become very difficult to solve that. So like I mean, at the end of the day, we tuned a lot of parameters to find something that would produce somewhat interesting, balanced solutions. Like one issue is like if the size of the goal region is too small and the capture radius is very large, then you can just sit at you can goaltend essentially and just sit at the goal and just stay there. And it's not an interesting video to look at, but it is like an optimal strategy, right? So basically this parameter space creates like super rich, unexpected games, like actually. So it was really fun to play with these parameters and see just like the robots discover new solutions. When we were running these experiments, we would just hit run, have no idea what was going to happen, and just watch the robots like try something. So I thought that was a pretty rewarding experience. One of the things is we also so one of the things that's weird about the retarget avoid game for dynamical systems, this was for a double integrator, is there's no known analytical solution to that. There's analytical solutions to the single integrator. So we didn't have like a verification that our method was actually working. So we validated on this game called the homicidal chauffeur game, which is like an analytical, it's a differential game with a known analytical solution. And so we were able to just like validate that the trajectories produced by our algorithm were matching the analytical solution.
That's pretty cool. And extending on that, because you actually are able to do it with quadcopters, which are not simple dynamical systems. Fantastic. Any other questions from the audience? In that case, I'm gonna thank you again, Benjamin, and thank you to Krishna for the wonderful presentations.